Hello, my name is Dylan Sleeper,
And my name is Diana Varuni.
and together we worked on a robotic system that plays air hockey.
Here's the setup. We have an air hockey table, a puck, and paddles welded to each of two robotic arms positioned at either side of the table. One RGBD camera sensor looks down on the table from the top of the scene. Our goal is for the robots to play a continuous game of air hockey. At regular time steps, we need to determine the position of the puck on the table. We use color filtering to isolate the point cloud points corresponding to the puck. Then we project those points into the world frame to calculate the puck's pose. In our gameplay algorithm, this was our first attempt at predicting the puck's trajectory. We extend the line of the puck's path to the side wall and assume that it bounces off at the same angle and velocity. So we construct a new line and move the paddle to intercept the puck. However, in reality, the puck bounces off at an unpredictable angle, likely due to its spin and material properties. So that attempt failed.
For our final algorithm, we start in the same exact way. We perform trajectory prediction and then move the paddle to where we think the puck is going to go. We still do this because we hope this prediction is at least somewhat close to where the paddle needs to be, so we don't have to move it as far. Now this is where the difference arises. We wait for a wall hit. Once the puck hits the wall, which we can detect by detecting a sudden change in velocity, we reperform this trajectory prediction. If our new trajectory doesn't have any sidewall hits in before it will reach the paddle, then we actually aim to hit the puck. We do this by constructing what we call a hit line, and then we detect when and where the puck is going to intercept that hit line. We draw then its velocity trajectory a little bit further and aim to put the paddle there. However, if we just swung from this position, the games would be pretty boring because both arms would just hit the puck back and forth to each other at the same trajectory. So we add a little bit of a random offset to this position, so the games are a little more varied and exciting. After doing this, we recalculate a trajectory such that the paddle will hit the puck at the right time in the right position. And then we send the puck away and repeat the process for the other arm. Now, let's actually check out this system in action. This first video is an example of our system playing a little bit slower than possible, but very consistently. You can see here, however, that the arms actually sometimes intersect themselves. This is because we're using the pseudo-inverse controller, which doesn't take the arm's own collisions or collisions with the table into an account. Now, we tried cranking up the speed a little bit, but when you crank it up too much, you sometimes get games like these, which are a little fast. Our arm isn't really able to keep up with the puck when it's moving that fast. It isn't able to react. And because we're moving so quickly, the trajectories are somewhat inaccurate. So it often just hits the puck into its own goal. However, with exactly the right tuning of these parameters, you can get some pretty exciting games like this one. Now, as you saw, sometimes it does miss, but really that sort of just adds to the excitement of the game. And most of the time when it does miss, it just hits the back wall. All in all, we think with parameters like this, it's much more interesting than the first video we showed. So in conclusion, we have a system that works. The main thing we want to improve is the controller. Currently, we wouldn't be able to use this on real robots because the robots would try and perform trajectories that collide with themselves and with the table. But if we actually used a controller that took those two things into consideration, we could actually deploy this on real robots. Thank you for listening.